So since we have a few minutes for discussion, I wanted to sort of and it's a little bit weird in this format. We've had a lot of great questions that are being answered in the conference.io, so please continue that. But I wanted to sort of prime the discussion for the folks who have gone today. Wesley, do you want to ask the question or do you want me to?
Oh, sure. I can take a stab, and then if you clarify where I get it wrong.
Sure.
No, so we are, as we're talking about modeling and simulation, one of the questions that comes up a lot of the times is gaps, modeling gaps. And so as a way of just sort of fostering discussion, if you could answer one question or make one measurement, or what is a sort of a critical gap to the modeling process right now that you would be willing to just share or throw out there?
One
Um,
thing. You only
one
get to
thing,
pick one.
even though there may be several. So I think anyone who is a panelist now should be able to unmute. And then if there's anyone who would like to put something in chat to the panelists, we can, as that comes up, please, we can read those. But where do you see, gaps but one thing to focus on?
So this is Parvati. So for me, I would say I would like to know how different kinds of exhaust gases interact with the lunar regolith. What's like the absorption activation energy? Do those gases fully thermally accommodate when they're coming in at high speeds? And, exhaust gases, so including H2O, CO2, other nitrogen and carbon things.
Interesting. Yeah, so that ties a little bit to some of the work that Dan Batchelor talked about in terms of like permeability and actually doing experiments with different gases. But yeah, that's cool.
So what I would say is a critical gap is the transition in granular flow regimes. As I sort of said yesterday in the little breakout session, there is, and this is from the literature, there's no physical basis on the transition from kinetic collisional to frictional regime. So there's a huge gap there, and not only from modeling perspective, but in the experiments, it's just really difficult to see what's going on there. So if you really want to go after something, that's a not only a NASA issue, that's a fundamental granular issue.
Sure. Yeah, that's something for our upcoming ground test. Transition between regimes is an area of critical interest there.
I would say, this is just that Ellen, I would say that it's important to have experimental measurements that can discriminate among models, because there are some experimental measurements that are such a global sort of extent that basically a lot of models will agree with it. So if you want to know where the physics is, one has to identify regions where specific models will give different results. And I think this is one thing that I have not seen in terms of comparing with models. I know it's very difficult to get results, experimental observations or diagnostics working in some regions of the flow, but those more challenging regions of the flow are those that must be addressed. And we have published a paper recently in the AIA journal, and we have a paper that's just about to be published in another journal, where we have made a definite effort to connect with experiments. We've taken several models and saying, we don't know which one is correct. Let's see where you can simulate, in other words, sensitivity of the model to certain inputs, certain submodels, and let's see what the experimentalists find. I think this is something that is very important. Like, for example, if you take the rogue test, which is an excellent set of measurements, but it's one-dimensional. And we've seen that there's so many models that compare favorably with it that is really not very discriminating. So I would say that this is where I see the challenge in terms of comparing experiments and simulations.
Yeah, and yeah, no, that's a really interesting point. I think with that and you know, since we have to in simulations kind of, or well, in both experiments, we're also choosing, you know, which things can we represent most accurately. So yeah, choosing those things and figure out how do we best, simulate in a way to understand that we're capturing the relevant physics. It's a really good point. Other thoughts?
Not only relevant physics, because I'm sure that a lot of measurements do capture relevant physics, but I would call here discriminating.
Yes.
Discriminating, something that will give you that, and it's not an easy thing to do, but I say that's what needs to be done.
Sure.
Yep. Well,
you can tease
one
some of that out
more
with actual sensitivity studies. I mean, I've published too, doing it intrusively, so you can get some of that parameters out. It's to Josette's point, working with experimentalists to actually have key things that we can both simulate and experiment and have all the things I think are really important.
Cool. Great. And I think one of our so reminder to everybody that there is a poll open right now in the conference IO for suggestions for breakout sessions today. And I maybe put one or two options in there already, but other people have as well. But one of the things we could use one of the breakout sessions to do is talk a little bit more about that, like how do we bridge those connections between different folks. And one of the things I want to talk about a little bit in the wrap up too is how do we continue more broadly this conversation amongst this group of people and others. So, okay. Are there anybody with one last hot take on this answer before we switch to the next session? Nobody? That was like a spur of somebody to say we really need to know temperature. No.
I'll throw out there that you know, going back to yesterday, the variation in local regolith properties and understanding that better. You know, we talk a lot about plumes and everything. You know, I think there are also some residual unknowns in terms of just ground truth data of the lunar surface. So
yeah,
elaborate, but yeah.
Hey, Kristen. All right. Well, thank you, everybody. And thanks to all of our speakers from the day thus far.